Hi, and welcome to Module 10 of a brief introduction to game theory. In this final module, we're going to discuss how to take our theory that we've been developing to data, to experiments. In the previous module, as well as a couple of modules ago, we talked about deviations of our model's predictions from real behavior among at least experimental subjects. But we haven't really talked about how to go about measuring these deviations and seeing if they exist or not. And for that, we're going to connect our games, our theoretical models of reality, to experiments in the lab. The first step of doing this is to, of course, derive your theory, right? Write your model that captures the world as you think it is, at least the simplification of the world as you think it is. Once you've done that, you want to derive hypotheses from your model that you can test. Hypotheses in the context of game theory often take the form of comparative statics. It's a kind of odd word, so let me unpack that a little bit. Equilibria in a game theory model are static. They are unchanging patterns of behavior such that if each person is playing equilibrium, no one has incentive to change behavior. Comparative statics is a way of saying we're comparing these static equilibria to other static equilibria that differ based on some exogenous parameters, some exogenous, external to the model, characteristics of the system, of the context, of individuals, or whatever, that when they vary, alter potentially the equilibrium that is played in the model. Let me give you an example of that we did a few modules ago. Let's go back to the altruistic prisoner's dilemma. So we had cooperation defect here, and we had payoffs that looked like this. If both individuals were equally altruistic, and if you don't remember this, you can go back to the module 7, I believe it was. Don't quote me on that. And the payoffs look like this. Okay, so A here is a degree of altruism on the part of both actors. In this context, A is an exogenous parameter. It's external to the game itself. The game doesn't fix the value of A, so A is not endogenous. The game itself doesn't determine how altruistic you are or not. You come into the game a certain level of altruistic. The game just translates the level of altruism on the part of the participants in the game to different equilibrium outcomes. A comparative static compares the equilibrium, the static equilibrium, across different values of this exogenous parameter. In this case, we have two possible outcomes of this model. When A is less than a half, defection is still a dominant strategy, and the only equilibrium is defect-defect. So, in that case, we have A less than a half, we have defect-defect. And for A greater than a half, we learned that we have only one equilibrium. Cooperation is dominant, so we have cooperate is the only one. On the knife edge case, when A equals a half, we actually could have both equilibria possible. Both are possible equilibria. But again, this happens in a knife edge situation. It's only true with the exact case that A is exactly equal to 1/2, which is unlikely to happen in general. Okay, so what does this mean? Now, this is not continuously changing, so it's a little tricky to discuss how our equilibrium changes with the parameter A. But in general, we might wave our hands a little bit and say, when A is small, we believe that there'll be defection in our game. When A gets bigger, at some point, we believe there'll be cooperation in our game. So we can construct a comparative static that says as A increases, we are more likely, and that's a little loose in that terminology, but we'll go with it for now. As A increases, we are more likely to have cooperation observed in our game. And that comparative static translates directly into a hypothesis. As the degree of altruism gets bigger among our participants in the game, cooperation is more likely to happen. Okay. So this gives us a sense of how to set up a theory and hypotheses from the solutions to our theory. And we can have any kind of parameters we want in a model, and we can find comparative statics for any exogenous parameter. So comparative static in general is just the way in which the equilibrium changes as a function of one or more exogenous parameters of the model. Okay. Once we've done that, we want to design a simple, short experiment to test our theory, our hypotheses. Now, in this case, test the hypotheses, in this case, we already have a very simple game, right? It's a simple PD. You gather people together, they play the game, they either cooperate or not. So we could probably run this game as is in a lab. For more complicated theoretical models, we might have to simplify our model to get a game that will run in the lab, because we need something that runs pretty quickly and is understandable in a short time period by the participants in the lab game. In this case, again, you could probably run it directly. Once you've either used the exact model you have from before or designed the simple short experiment such that people can follow along successfully, then it's time to make sure your experiment sort of satisfies the needed desiderata, right? What do you need the experiment to do? And the most important thing is it should be controlled. It should be a controlled experiment in the sense you don't want outside factors to affect the actor's choices beyond what you put in the model, in the experiment itself, right? It would do you no good if the behavior was driven not by the level of altruism of the respondent or by the payoffs in the game itself, but instead by what everyone had for breakfast that day, right? That would not be a good model, right? That's, again, a silly example, but breakfast here stands in for any characteristic of individuals or of the context that they're playing in, the game in, that might affect their behavior and their choices within the game in ways you don't want. Similarly, as part of this control, you want to vary at most one parameter at a time. You don't want to vary everything at once, because then you can't figure out how to attribute behavior. Like, how do you know which of these many things you varied at once is the cause of the change in behavior? Both these really get at what we're trying to do here, which was to mimic as much as possible a classical randomized controlled trial experiment in which we have a treatment group and a control group that are the same in all possible ways, except the treatment group has a difference that the control group does not, the treatment, right? You're probably familiar with this in terms of medical experiments in which you give one group whatever medical treatment you're trying to test, and the other group, the control group, you don't, and then you compare at the end of this differences in health outcomes between the treatment and the control groups, as well as side effects. We're trying to do the same kind of thing. We're trying to say, for instance, compare everyone's the same across two different groups. One group has low altruism, somehow exogenously defined, right? And the other group has high altruism, and we're trying to see if the high altruism group cooperates more than the low altruism group, or individuals in the high altruism group manage to cooperate more than the low altruism group. In that case, the treatment is a level of altruism. Now, in practice, it's kind of hard to do that a lot of the time because we can't actually assign altruism. One of the nice things about lab experiments in game theoretic terms is that we can assign payoffs and compare how altruism works in that sense, right? We can force A to change. We can give one group a higher A than another group and see if they cooperate more. And that mimics the underlying notion of altruism in this case. To get to this randomized controlled trial, we want to randomly assign our subjects to groups. We don't want groups of one characteristic to all be in the same treatment group or control group, and people of the same characteristic to be in a different group. That would be bad because then that different characteristic might be driving results in a way we don't want. Instead, we want to randomize all our individuals who are going to take part in this experiment across the treatment and control groups randomly. So finally, besides that, we want to make sure our experiment itself is clearly stated. Games are often difficult to understand, as you might know quite well after going through this lecture, this series of modules. And so it's important when you're presenting people who have not seen any kind of game before to go slowly through your rules and your requirements and keep the game simple, but also explain it clearly so people can follow the directions, because what you don't want is for people to play in a way different from what you expected, not because of some effect of a parameter's difference, not because they're more altruistic, say, or less altruistic, but rather because they have some uncertainty or unclarity about, lack of clarity about what the game means. They're just messing up, right? That can be informative to know they're messing up, but in general, it's not what you're going for in this carefully set up lab experiment. That's pretty much it. The only thing I'll mention in closing is measurement is key here as well. If you don't assign altruism by just saying you have an A of 2 and you have an A of 1 or whatever, you're going to have to measure altruism levels, and that requires a good measurement of altruism. There are a lot of existing measures of things like risk preferences and altruism stuff in the literature, so it's good to look into the literature to see what's already out there in terms of measurement, both because it saves you time and because it gives you some level of validity that other individuals have used it successfully before. Okay. Well, that is it for this lecture, this module, and this lecture. Thank you very much for watching.